When the James Webb Space Telescope released its first images to the world in July 2022, people everywhere were stunned by the beauty and clarity of what they saw. But those images weren't just pretty pictures meant to wow the public. Hidden within those first photos were scientific secrets that scientists are still talking about today. These discoveries changed how we understand the universe, and they continue to matter years later because they opened doors to questions we didn't even know we should be asking. The first images included some of the most famous space photos ever taken. There was SMACS 0723, showing a cluster of galaxies that acted like a magnifying glass for even more distant galaxies behind it. The Carina Nebula revealed stunning detail in a stellar nursery where new stars are born. Stephan's quintet showed 5 galaxies interacting with each other in ways that tell us about galactic evolution. The Southern Ring Nebula displayed the beautiful but sad death of a star. And there was also a spectrum from an exoplanet atmosphere, proving Webb could study planets around other stars. Each of these images contained surprises that went far beyond what anyone expected. Scientists thought they knew what they would see, but Webb showed them things that challenged existing theories and forced everyone to think differently about space. The story of why these images matter starts with understanding what made Webb different from every telescope that came before it. For decades, the Hubble Space Telescope was humanity's eye in the sky. Hubble orbits Earth and observes the universe mainly in visible light, the same light our eyes can see. It revolutionized astronomy and gave us iconic images that changed how we see the cosmos. But Hubble had limitations. It couldn't see through cosmic dust very well. It couldn't observe the most distant and ancient parts of the universe effectively. And it couldn't study cool objects that don't shine brightly in visible light. Webb was designed specifically to overcome these limitations. Instead of observing in visible light, Webb observes primarily in infrared. Infrared is heat radiation. Everything that has temperature emits infrared light. The warmer something is, the more infrared it emits. By observing in infrared, Webb can see through dust clouds that block visible light. It can detect objects so far away that the expansion of the universe has stretched their light from visible wavelengths into infrared wavelengths. And it can study cool objects like brown dwarfs and distant planets that barely shine in visible light but glow warmly in infrared. To detect faint infrared signals from across the universe, Webb itself needs to be extremely cold. If the telescope were warm, its own heat would overwhelm the faint signals it's trying to detect. This is why Webb orbits at a special location called the second Lagrange point, about 1.5 million kilometers from Earth in the direction away from the Sun. At this location, Webb stays in Earth's shadow, protected from the Sun's heat by a massive sunshield the size of a tennis court. This shield has 5 layers that create an extreme temperature difference. The sun-facing side gets scorching hot, but the telescope side stays colder than -200 degrees Celsius. This frigid temperature is essential for Webb's sensitive infrared detectors to work properly. Webb's mirror is also special. At 6.5 meters across, it's much larger than Hubble's mirror. Size matters for telescopes because bigger mirrors collect more light, allowing you to see fainter and more distant objects. Webb's mirror isn't a single piece. It's made of 18 hexagonal segments that work together as one mirror. Each segment is coated with a microscopically thin layer of gold because gold reflects infrared light extremely well. The segments can be adjusted individually with incredible precision, keeping the entire mirror perfectly aligned despite the harsh conditions of space. When scientists released Webb's first images, they chose targets carefully to showcase the telescope's capabilities. But even the scientists were surprised by what Webb revealed. The images contained scientific secrets that nobody fully anticipated. These weren't minor details. They were fundamental discoveries that raised new questions about how the universe works. The first major secret was hidden in the image of SMACS 0723. This image showed a galaxy cluster, which is a collection of hundreds or thousands of galaxies held together by gravity. The cluster itself wasn't the main story. Galaxy clusters have a special property that makes them incredibly useful to astronomers. Their enormous mass bends space itself, creating what's called gravitational lensing. Light from galaxies far behind the cluster gets bent and magnified as it passes through the warped space around the cluster. This turns the cluster into a natural telescope. allowing us to see galaxies that would otherwise be too faint and distant to detect. Hubble had observed this same galaxy cluster before. Scientists knew what to expect. They anticipated Webb would show more detail and perhaps reveal a few more distant galaxies. But what Webb actually showed stunned everyone. The image revealed hundreds of extremely distant galaxies, many of them appearing as tiny red dots scattered across the background. These weren't just any distant galaxies. Many of them existed when the universe was less than 1 billion years old, in the earliest era of cosmic history. The secret hidden in this image was about galaxy formation in the early universe. Based on previous observations and computer models, scientists thought they understood how galaxies formed. The theory suggested that in the very early universe, galaxies should be small, messy, and irregular. They hadn't had enough time to grow large or develop organized structures. Small galaxies would gradually merge together over billions of years to form the large, organized galaxies we see in the nearby universe today. But Webb's image showed something unexpected. Some of those ancient, distant galaxies looked surprisingly mature and organized. They had clear structures. Some appeared to have disc shapes similar to spiral galaxies. Some seemed to have central bulges. These features indicated that these galaxies were more evolved than they should have been. It was like finding a fully grown oak tree in a forest that had only existed for a few years. The tree shouldn't have had time to grow that large yet. This discovery created what some scientists called a crisis in cosmology. If galaxies could become large and structured faster than our models predicted, then something fundamental about our understanding of galaxy formation must be wrong. Maybe dark matter behaves differently than we thought. Maybe stars formed more efficiently in the early universe. Maybe galaxies merged together faster than expected, or maybe there were processes happening in the early universe that we don't understand at all. This secret matters today because it's driving a huge amount of current research. Astronomers are using Webb to observe even more distant galaxies, trying to understand when and how they developed their structures. Theorists are revising their computer models, testing different scenarios to see what could explain the observations. And everyone is realizing that the early universe might have been a much more dynamic and interesting place than we thought. The second major secret was hidden in the Carina Nebula image. The Carina Nebula is a stellar nursery, a giant cloud of gas and dust where new stars are being born. It's located in our own Milky Way galaxy, about 7,000 light-years from Earth. Hubble had photographed this nebula before, producing beautiful images of towering pillars of gas illuminated by brilliant young stars. Scientists chose this target for Webb because they wanted to show how the telescope could peer through dust and reveal the hidden processes of star formation. What Webb revealed was extraordinary. The image showed incredible detail in the structure of the nebula. Towering cliffs of gas seemed to glow with golden light. Behind these cliffs, dozens of previously hidden young stars became visible. Webb could see through the dust that hides these stars from visible light telescopes. But the real secret wasn't just about seeing more stars, it was about what was happening around those stars. Webb detected numerous jets and outflows streaming away from newborn stars. When a star forms, it doesn't quietly condense from a cloud. The process is violent. Material falls toward the forming star, but not all of it ends up in the star. Some gets ejected in powerful jets that shoot out from the star's poles at incredible speeds. These jets plow through the surrounding gas, creating shock waves and clearing out cavities. They can trigger or prevent the formation of new stars nearby, depending on how they interact with the surrounding material. Previous telescopes had seen some of these jets, but Webb revealed them in unprecedented detail and found many more than expected. The secret was that star formation is even more chaotic and dynamic than scientists thought. The jets varied wildly in their properties. Some were narrow and fast, others were wide and slow. Some seemed to pulse, varying in strength over time. This variability suggested that the star formation process involves complex physics that current models don't fully capture. The jets also revealed information about the chemistry of star-forming regions. Webb's instruments could analyze the light from the jets to determine what molecules were present. Scientists found water vapor, which was expected since water is common in space. But they also found more complex molecules, organic compounds containing carbon that are the building blocks for more complex chemistry. The abundance and variety of these molecules was greater than anticipated. This discovery connects to questions about how common the ingredients for life might be throughout the universe. This secret matters today because understanding star formation is fundamental to understanding where planets come from. Stars don't form alone. The disk of material around a forming star is where planets coalesce. By studying the star formation process in detail, scientists learn about the conditions under which planetary systems develop. The complex chemistry revealed by Webb suggests that the building blocks for planets and potentially life are distributed widely during star formation. This has implications for understanding how our own solar system formed and whether planetary systems with complex chemistry are common or rare. The third major secret emerged from the image of Stephan's quintet. This is a group of 5 galaxies that appear close together in the sky. 4 of them are actually interacting with each other, engaged in a slow-motion cosmic collision. The 5th galaxy is much closer to us, and only appears to be part of the group from our perspective. Galaxy interactions like this are important for understanding how galaxies evolve. When galaxies collide, their gravity stirs up gas and triggers intense bursts of star formation. Over billions of years, mergers between galaxies help build the large galaxies we see in the nearby universe. Hubble had observed Stephan's quintet before, and scientists knew what the image should show. They expected Webb to reveal more detail about the star-forming regions triggered by the interaction. They anticipated seeing shock waves in the gas where the galaxies were colliding. What they didn't expect was what Webb found at the heart of one of the galaxies. Hidden in the center of one galaxy was an actively feeding supermassive black hole. Black holes are regions of space where gravity is so strong that not even light can escape. Supermassive black holes, weighing millions or billions of times the mass of our Sun, sit at the centers of most large galaxies, including our own Milky Way. These black holes can be quiet, barely affecting their surroundings, or they can be actively feeding, pulling in gas and dust from around them. When a black hole actively feeds, the infalling material doesn't fall straight in. It swirls around the black hole in a disk, heating up to tremendous temperatures through friction. This superheated material shines brilliantly across the electromagnetic spectrum, often outshining all the stars in the galaxy combined. The region around an actively feeding black hole can also produce powerful jets that shoot material out at nearly the speed of light. The secret Webb revealed was that the black hole in Stephan's quintet was much more active than previous observations suggested. Webb could see through the dust surrounding the black hole and detect the hot gas swirling around it. The black hole was pulling in material disturbed by the galaxy collision. This feeding was energetic, releasing enormous amounts of energy that heated the surrounding gas and possibly affected star formation throughout the galaxy. What made this discovery particularly interesting was what it revealed about the connection between galaxy mergers and black hole growth. Scientists have long suspected that galaxy collisions play a role in feeding supermassive black holes. When galaxies collide, the gravitational chaos can funnel gas toward the center, providing fuel for the black hole. But observing this process in action has been difficult because dust often obscures the view. Webb's infrared vision allowed scientists to peer through the dust and watch the feeding process happening in real time. This secret matters today because it helps solve a long-standing puzzle about how supermassive black holes grow. Astronomers have found supermassive black holes in very distant, very young galaxies. These black holes are surprisingly large for how young the universe was when they formed. Scientists have struggled to explain how black holes could grow so large so quickly. The Webb observations of Stephan's quintet show that galaxy interactions can rapidly feed black holes, causing them to gain mass much faster than they would in isolated galaxies. This suggests that frequent mergers in the early universe might be the key to understanding how supermassive black holes grew so large so fast. The fourth major secret came from the Southern Ring Nebula image. A planetary nebula, despite its name, has nothing to do with planets. It's the beautiful but brief final stage in the life of a medium-sized star like our Sun. When such a star exhausts its nuclear fuel, it puffs off its outer layers in a series of pulses. These ejected layers expand into space, creating a glowing shell of gas illuminated by ultraviolet light from the hot core of the dying star. Eventually, the core cools and fades, and the nebula disperses into space, leaving behind only a white dwarf, a dense remnant about the size of Earth, but with a mass similar to the Sun. Hubble had photographed the Southern Ring Nebula before, producing beautiful images showing the symmetric structure of the expanding gas shell. Scientists understood the basic process of how planetary nebulae form. But Webb's observations revealed a secret that changed this understanding. Webb showed that the Southern Ring Nebula was not created by one star, but by two stars orbiting each other. The nebula's complex structure, with multiple shells and arcs of gas, could only be explained if a binary star system created it. One star went through its death process first, ejecting its outer layers. But the presence of the companion star affected how those layers were ejected. The gravity of the companion distorted the outflows, creating asymmetries and complex patterns in the nebula's structure. This revelation was important because it suggested that binary stars might play a much larger role in creating planetary nebulae than previously thought. Scientists had assumed most planetary nebulae came from single stars. If many actually come from binary systems, it changes our understanding of how common binary stars are and how they affect stellar evolution. But Webb revealed an even deeper secret. The detailed observations showed that the dying star had gone through multiple mass loss episodes. The gas wasn't ejected all at once. Instead, the star pulsed several times, each pulse ejecting a shell of material. The shells expanded at different speeds, and where faster shells caught up with slower shells, they created dense regions that glowed brightly in Webb's infrared view. This complex mass loss history revealed something important about the death process of stars. The final stages of stellar evolution are chaotic and variable, not smooth and predictable. Stars don't die quietly. They go through dramatic changes, sometimes rapidly, before finally exhausting their fuel. Understanding this process is important for understanding how elements are distributed through space. When stars die, they scatter into space all the elements they created during their lives through nuclear fusion. These elements, including carbon, oxygen, and nitrogen, are essential for planets and life. The way stars distribute these elements depends on the details of how they die. This secret matters today because it's changing how scientists model the end stages of stellar evolution. Computer models need to account for the complex, variable nature of mass loss. They need to consider the effects of binary companions, and they need to explain the chemical patterns Webb observed in the nebula's gas. Better models will help us understand the cosmic cycle of matter, how elements created in stars end up in new stars, planets, and eventually living things. The fifth major secret was revealed not through an image, but through a spectrum of an exoplanet's atmosphere. An exoplanet is a planet orbiting a star other than our Sun. Thousands of exoplanets have been discovered over the past few decades, revolutionizing our understanding of planetary systems. But discovering an exoplanet is one thing. Studying its atmosphere is much harder. To study an exoplanet's atmosphere, astronomers use a technique called transit spectroscopy. When a planet passes in front of its star, from our point of view, a tiny fraction of the star's light passes through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb light at specific wavelengths. By carefully analyzing the spectrum of light during the transit, scientists can determine what molecules are present in the planet's atmosphere. Webb observed the exoplanet WASP 96b, a hot gas giant planet orbiting very close to its star. Hot Jupiters like this don't exist in our solar system, but they're common around other stars. Scientists wanted to demonstrate that Webb could study exoplanet atmospheres with unprecedented precision. What they found was remarkable. Webb detected clear signs of water vapor in the planet's atmosphere, which was expected, but it also detected something unexpected. The spectrum showed evidence of clouds or haze in the atmosphere. The signature of water vapor was partially blocked or muted by something obscuring it. This indicated that the planet's atmosphere was not clear, but contained particles suspended high in the atmosphere. The secret was in the details of those clouds. By analyzing exactly how the light was affected, scientists could determine properties of the cloud particles. They learned about the size of the particles, their composition, and their distribution in the atmosphere. The particles were different from what simple models predicted. They suggested that the chemistry in hot Jupiter atmospheres is more complex than expected, with chemical reactions creating exotic compounds that don't exist in cooler atmospheres like Earth's. This discovery opened up a new era in exoplanet science. Before Webb, studying exoplanet atmospheres was difficult and limited. Instruments could detect only the most abundant molecules, and results were often ambiguous. Webb's sensitivity and spectral resolution allowed detailed characterization of atmospheric composition and structure. This capability matters today because it's being used to study many different exoplanets, building up a census of what exoplanet atmospheres are like. The long-term goal is to study smaller, cooler planets more similar to Earth. Webb has the capability to detect biosignatures, molecules like oxygen or methane that could indicate biological activity in the atmospheres of nearby Earth-sized planets. Finding such signatures would be one of the most important discoveries in human history, suggesting that life exists beyond Earth. The spectroscopic techniques demonstrated with JWST-96b are paving the way for these future observations. These 5 secrets hidden in Webb's first images share a common theme. They all revealed that the universe is more complex, more dynamic, and more interesting than our models predicted. The early galaxies were more mature. Star formation was more chaotic. Galaxy interactions fed black holes more efficiently. Stellar death was more variable. Exoplanet atmospheres were more complicated. In every case, Webb showed us that nature is cleverer than our theories. This pattern has continued in the years since those first images were released. Webb has made discovery after discovery, each one revealing new secrets about the cosmos. It has found the most distant galaxies ever observed, pushing back our view to when the universe was only a few 100 million years old. It has studied the atmospheres of dozens of exoplanets, revealing surprising diversity in their compositions. It has peered into star-forming regions, watching planets being born. It has observed supermassive black holes at unprecedented distances, helping us understand how these monsters grew, and it has found organic molecules in places we never expected, changing our thinking about the distribution of life's building blocks. The reason Webb's first images still matter today is that they set the template for everything that came after. They demonstrated Webb's capabilities and showed scientists what kinds of discoveries were possible. They revealed that the universe was ready to surprise us if we had the tools to look carefully enough. And they inspired a generation of astronomers to ask bigger questions and design more ambitious observation programs. The first images also mattered for another reason. They captured public imagination in a way that few scientific results ever do. The beauty of the images drew people in. The stories behind them kept people interested. Millions of people who normally don't pay attention to astronomy found themselves curious about galaxy formation, star death, and the search for life beyond Earth. This public engagement is valuable because it builds support for science and inspires young people to consider careers in science and engineering. The technological achievement represented by Webb cannot be overstated. Building a telescope that could fold up to fit inside a rocket, travel 1.5 million kilometers from Earth, unfold perfectly in space, keep itself colder than -200 degrees Celsius, and maintain precise alignment of 18 mirror segments is an engineering marvel. The fact that it worked on the first try is extraordinary. Many things could have gone wrong during deployment. Any one failure would have ended the mission. But everything worked, a testament to the skill and dedication of the thousands of engineers and scientists who designed and built it. Webb was decades in the making. The concept was proposed in the late 1990s. Construction began in the early 2000s. The original launch date was supposed to be 2011, but technical challenges and budget issues caused repeated delays. By the time Webb finally launched in December 2021, many people who worked on it had spent their entire careers on the project. The successful deployment and the stunning first images were vindication for all that effort. The cost of Webb was substantial, about $10 billion over its lifetime from concept to launch and operation. Critics sometimes question whether such expensive projects are worth it, but the scientific and technological returns are enormous. Webb is providing data that will fill textbooks for decades. It's answering fundamental questions about the universe and raising new questions we couldn't have asked without it. The technologies developed for Webb have applications in medicine, industry, and national security. And the inspiration it provides to young people considering careers in science and engineering is immeasurable. Understanding why Webb's first images still matter requires understanding how science works. Scientific progress is not a straight line. It's a process of asking questions, gathering data, revising theories, and asking new questions. Each discovery builds on previous discoveries. Each new instrument enables observations that weren't possible before. Webb stands on the shoulders of all the telescopes that came before it, from Galileo's simple telescope 400 years ago to Hubble's sophisticated space observatory. And the discoveries Webb makes will enable future instruments to go even further. Several next-generation telescopes are already being planned. Some will be ground-based telescopes with enormous mirrors 30 meters or more in diameter. These will have the resolution to study nearby exoplanets in detail and observe the earliest galaxies. Others will be space-based telescopes designed to succeed Webb. One concept is a telescope specifically optimized for finding biosignatures on exoplanets. Another is a telescope designed to study the very earliest moments of cosmic history, looking back to when the first stars formed. These future instruments will build on what Webb has taught us. Webb's first images also matter in a historical sense. They represent a moment when humanity's view of the universe expanded significantly. We're living through a golden age of astronomy. In just the past few decades, we've discovered thousands of exoplanets. We've detected gravitational waves from colliding black holes. We've imaged the event horizon of a supermassive black hole. We've traced the cosmic web of dark matter that structures the universe. And now Webb is showing us the early universe and the atmospheres of alien worlds in unprecedented detail. Future historians will look back on this era as a time when our understanding of the cosmos grew dramatically. The first images remind us that exploration is a fundamental human drive. For all of human history, we've been curious about what's beyond the horizon. We've explored our planet, mapping every continent and ocean. We've sent spacecraft to every planet in our solar system and landed rovers on Mars. We've sent probes beyond the edge of the solar system into interstellar space. And through telescopes like Webb, we're exploring the entire observable universe, looking back in time to the earliest moments of cosmic history. This drive to explore and understand is part of what makes us human. The secrets hidden in Webb's first images also remind us how much we still don't know. Despite centuries of scientific progress, the universe remains full of mysteries. We don't understand what dark matter is, even though it makes up most of the matter in the universe. We don't know what dark energy is, even though it's causing the universe's expansion to accelerate. We don't know how the first stars and galaxies formed. We don't know how common life is in the universe. We don't know whether we're alone. These are profound questions, and Webb is helping us make progress on answering them. Each of the 5 secrets revealed by Webb's first images opened up new lines of research that continue today. The mature early galaxies motivated a surge in theoretical work trying to explain how galaxies could evolve so quickly. The chaotic star formation revealed new physics that need to be incorporated into models. The active black hole feeding showed how galaxy mergers drive black hole growth. The complex stellar death processes demonstrated the need for better models of stellar evolution. And the cloudy exoplanet atmosphere kicked off a systematic study of exoplanet atmospheric composition. All of these research programs are ongoing, with new papers being published every week. The first images also demonstrated something important about scientific communication. When the images were released, NASA and other space agencies didn't just show pretty pictures. They provided context, explaining what the images showed and why it mattered. Scientists gave interviews to explain the significance of the discoveries. Educational materials were created to help teachers bring these discoveries into classrooms. Social media was used to engage with the public directly. This comprehensive communication strategy helped ensure that the discoveries reached beyond the scientific community to the broader public. The international collaboration that made Webb possible deserves recognition. The telescope was built through a partnership between NASA, the European Space Agency, and the Canadian Space Agency. Scientists and engineers from dozens of countries contributed. The observation programs include researchers from around the world. This international cooperation shows what humanity can achieve when we work together toward common goals. The data from Webb is freely available to scientists everywhere, ensuring that the benefits of the mission are shared globally. The first images also matter because they set a standard for scientific visualization. The images are not just data dumps, they're carefully processed to reveal structure and highlight features while remaining scientifically accurate. The colors are assigned to different wavelengths of infrared light. translated into visible colors our eyes can see. This processing takes skill and judgment. The teams responsible for creating these images balance scientific accuracy with aesthetic appeal, making images that are both informative and beautiful. These images have become iconic, appearing in textbooks, museums, and popular media. Looking back at Webb's first images from the perspective of a few years later, their significance becomes even clearer. They weren't just a demonstration of the telescope's capabilities, they were the opening chapter of a new book in astronomy. They set the stage for years of discoveries to come. They revealed that the universe was ready to teach us new lessons if we were ready to learn, and they inspired millions of people to care about space science and think about humanity's place in the cosmos. The story of Webb's first images is also a story about patience and perseverance. The telescope was decades in development. Launch was delayed multiple times. Once in space, deployment took months as hundreds of mechanisms worked perfectly in sequence. Commissioning the instruments took additional months of careful calibration and testing. Only after all this preparation could science observations begin. The first images were worth the wait, but they required extraordinary patience from everyone involved. The success of Webb's first images also validated the risk of building such an ambitious mission. Space telescopes are expensive and risky. They can't be repaired if something goes wrong. Hubble needed multiple servicing missions by space shuttle astronauts to fix problems and upgrade instruments. Webb orbits too far away for astronauts to reach. If something had failed, the mission would have ended. But NASA and its partners accepted this risk because the potential scientific rewards were so great. The spectacular success of the first images proved that the risk was worth taking. The legacy of Webb's first images will endure for decades. Students learning astronomy in the future will study these images the way current students study Hubble's deep fields. The discoveries they revealed will be featured in textbooks and taught in classrooms around the world. The images themselves will remain iconic, instantly recognizable even to people who don't follow space science closely. And the scientific questions they raised will motivate research for generations. The 5 secrets hidden in those first images remind us that the universe is full of surprises. No matter how much we learn, there's always more to discover. Each answer leads to new questions. Each solved mystery reveals deeper mysteries. This is the nature of science. We never reach a final answer. We just keep learning more, understanding more deeply, and asking better questions. Webb's first images advanced our understanding significantly, but they also showed us how much we still don't know. As we look to the future, Webb will continue operating for many more years. Its fuel supply should last a decade or more. During that time, it will make countless more discoveries. It will study the earliest galaxies in even more detail. It will characterize the atmospheres of dozens of exoplanets. It will watch stars and planets forming. It will observe supernovas and black holes. Each observation will add to our knowledge. And undoubtedly, there will be more surprises, more secrets revealed, more moments when scientists realize that the universe is even more interesting than they thought. The first images will always hold a special place in the story of Webb. They were the moment when years of planning and construction finally paid off. They were when the scientific community and the public first saw what this incredible telescope could do. They were when we got our first glimpse of secrets that had been hidden from us until we built the tools to reveal them. And they were when we realized that the universe was eager to teach us if we were ready to learn. So when you look at Webb's first images today, remember that you're not just looking at pretty pictures. You're looking at evidence of how galaxies formed in the early universe. You're seeing the chaotic birth of stars and the beautiful death of others. You're watching galaxies collide and black holes feed. You're glimpsing the atmospheres of alien worlds, and you're witnessing humanity's expanding understanding of the cosmos. These images changed astronomy. They continue to matter because the questions they raised are still being answered. They still inspire us to wonder about the universe and our place in it. That's why the secrets hidden in Webb's first images will continue to matter for years to come. If you enjoyed learning about the hidden secrets in Webb's first images, let us know which discovery surprised you most in the comments below. And if you want to keep up with the latest discoveries from Webb and other space missions, make sure to subscribe. There's so much more to explore, and we'll be covering every exciting new discovery as it happens. Thanks for watching, and keep looking up at the stars. The journey to creating Webb's first images began long Before the telescope launched, scientists spent years planning which targets to observe first. They wanted images that would showcase Webb's capabilities while also making significant scientific contributions. The choices needed to represent the different types of observations Webb could perform. Some targets should be nearby objects in our own galaxy. Others should be distant objects showing the early universe. Some should demonstrate imaging capabilities. Others should show spectroscopic capabilities. The selection process involved intense debate within the scientific community about which targets would provide the best demonstration of what Webb could do. The decision to include SMACS as 0723 was strategic. Galaxy clusters as gravitational lenses are a key scientific use case for Webb. The telescope was designed specifically to study the earliest galaxies, and gravitational lensing is one of the best ways to find them, by magnifying distant galaxies. The cluster acts like a natural telescope, bringing faint objects within Webb's reach. Scientists knew that this image would reveal distant galaxies. What they didn't know was just how many would appear and how surprising their properties would be. The preparation for observing SMACS 0723 involved careful planning of the telescope's pointing and the exposure time. The image required over 12 hours of integration time, collecting light continuously as the telescope stared at this patch of sky. This long exposure allowed Webb to detect extremely faint objects. The data was then carefully calibrated and processed, removing instrumental effects and cosmic rays. The final image represented the combined effort of engineers running the telescope, scientists planning the observations, and data processors creating the final product. When the image was revealed to the project team before public release, there was immediate excitement about the number of distant galaxies visible. Scientists quickly began analyzing the data, measuring the colors and brightnesses of the galaxies to estimate their distances. Some galaxies had colors indicating they were extremely far away. Follow-up spectroscopic observations were immediately planned to measure precise distances and study the properties of these galaxies in detail. The image wasn't just a pretty picture, it was a goldmine of scientific data that would keep researchers busy for years. The Carina Nebula was chosen as a first image target because it would demonstrate Webb's ability to peer through dust and reveal hidden star formation. This nebula is one of the largest and most active star-forming regions visible from the southern hemisphere. It contains massive young stars that are among the most luminous objects in our galaxy. These stars blast their surroundings with intense ultraviolet radiation, sculpting the gas and dust into dramatic shapes. Ground-based telescopes and Hubble had produced stunning images of this region, but scientists knew Webb would reveal new details thanks to its infrared vision. The observation strategy for the Carina Nebula involved multiple filters, each sensitive to different wavelengths of infrared light. By observing in several filters, scientists could create a detailed picture of the nebula's structure and composition. Different molecules emit light at different wavelengths, so multi-filter observations reveal the distribution of various chemical species. The resulting images could be combined to create color images that show the physical properties of different regions. When scientists saw the Carina Nebula image from Webb, they were struck by the level of detail. Features that appeared smooth in Hubble images were revealed to have intricate structure. The edges of dust clouds showed fine filaments and knots. The locations of embedded young stars were pinpointed with precision, and the jets and outflows from forming stars were visible in stunning clarity. The image immediately became one of the most popular from Webb's first release, with people marveling at what looked like golden cliffs of gas rising into a cosmic ocean. But beyond the beauty, the science in this image was profound. The jets revealed by Webb are crucial for understanding how stars regulate their own formation. When material falls onto a forming star, some gets ejected in these jets. The jets carry away angular momentum, allowing more material to fall onto the star. Without this process, the rotation of the infalling material would prevent the star from growing. By studying the jets in detail, scientists learn about the physics of accretion and ejection, processes that are fundamental to star formation. The chemical information in the Carina image also advanced our understanding of stellar nurseries. Webb detected molecules that are destroyed by ultraviolet light, surviving only in dense, shielded regions. The spatial distribution of these molecules maps out where the densest gas is located, which is where the next generation of stars will form. By combining Webb's observations with data from other telescopes observing different wavelengths, scientists can build a comprehensive picture of the star formation process from beginning to end. Stephan's quintet was selected as a first image target because it showcases Webb's ability to study galaxy interactions. Galaxies don't live in isolation, they interact with their neighbors, and these interactions drive galactic evolution. Small galaxies merge to form larger ones. Gas gets stirred up, triggering bursts of star formation. And supermassive black holes at galactic centers can be fed by material funneled inward during the collision. All of these processes are happening in Stephan's quintet, making it an ideal laboratory for studying galaxy evolution. The observations of Stephan's quintet used both imaging and spectroscopy. Images showed the overall structure and distribution of stars and gas. Spectroscopy analyzed the light to determine velocities, temperatures, and compositions. By combining these techniques, scientists could build a complete picture of what's happening in this system. They could identify regions of active star formation. They could measure the velocities of gas flows, showing material streaming between galaxies, and they could study the shock waves generated by the collisions. The discovery of the actively feeding black hole in Stephan's quintet was a highlight of the first images. Black holes are invisible themselves, but their effects on surrounding material make them detectable. The hot gas swirling around the black hole emits X-rays and infrared light. Webb detected the infrared emission, revealing the black hole's location and activity level. The observation confirmed that galaxy collisions can efficiently feed black holes, a process that may explain how some black holes grew so massive in the early universe. The Southern Ring Nebula was chosen to demonstrate Webb's capability to study stellar death. Planetary nebulae are both beautiful and scientifically important. They represent a brief but crucial stage in stellar evolution when stars return their processed material to space. The elements created through nuclear fusion in the star's core are scattered into the interstellar medium, where they can be incorporated into new generations of stars and planets. Understanding this process is key to understanding the chemical evolution of the galaxy. Previous observations of the Southern Ring Nebula showed a symmetric structure with a bright central star. But Webb's observations revealed much more complexity. The nebula had multiple shells and arcs, indicating several mass loss episodes. The structure was asymmetric, pointing to the influence of a binary companion. And the detailed spectroscopy showed how the chemistry varied throughout the nebula, with different elements concentrated in different regions based on when and how they were ejected. The binary nature of the system was particularly interesting. Binary stars are common, with perhaps half of all stars existing in binary or multiple star systems. But the effects of binary companions on stellar death are complex and not fully understood. The companion's gravity can distort the mass loss, creating the intricate structures seen in the Southern Ring Nebula. In some cases, the companion might even strip material from the dying star, affecting how much mass is lost and how it's distributed. The spectroscopic observations of the Southern Ring Nebula revealed details about the dying star's final stages. The spectrum showed emission lines from various elements including hydrogen, helium, nitrogen, oxygen, and neon. The strengths of these lines indicated the abundances of different elements, showing what the star had created through nuclear fusion during its life. The temperatures and densities of different regions could be determined from the ratios of emission lines. All of this information helps scientists understand the processes occurring in the nebula and how the material will eventually disperse and enrich the interstellar medium. The exoplanet observation that was part of Webb's first release demonstrated the telescope's capability for exoplanet characterization. JWST-96b is not a habitable world. It's a hot Jupiter, a gas giant orbiting so close to its star that its atmosphere is heated to over 1,000 degrees Celsius. But this planet was chosen precisely because its hot, puffy atmosphere makes it relatively easy to study. The techniques developed for this planet would later be applied to smaller, cooler worlds that are more interesting from an astrobiology perspective. The transit spectroscopy technique used for JWST-96b is elegant. As the planet passes in front of its star, about 1% of the star's light is blocked, causing a tiny dip in brightness. But not all wavelengths are blocked equally. If the planet has an atmosphere, some of the star's light passes through the atmosphere on its way to us. Molecules in the atmosphere absorb light at specific wavelengths. By comparing the spectrum during the transit to the spectrum outside the transit, scientists can identify which wavelengths are absorbed, revealing what molecules are present. Webb's spectrum of WSP-96b showed clear evidence of water vapor absorption. The water signature appeared as a broad absorption feature at specific infrared wavelengths, but the signature was muted compared to what a clear atmosphere would produce. This indicated the presence of clouds or haze high in the atmosphere. Additional analysis showed that the clouds were likely made of silicate particles, like tiny grains of sand suspended in the hot gas. These clouds formed through condensation of vaporized minerals in the extreme heat of the planet's atmosphere. The detailed characterization of WSP-96b's atmosphere was a proof of concept. It showed that Webb could extract detailed information about exoplanet atmospheres. The telescope could detect molecules, constrain cloud properties, and measure temperature structures. All of these capabilities would be crucial for studying smaller planets. The goal is eventually to study planets similar in size and temperature to Earth, looking for signs of habitability or even biosignatures that might indicate life. The biosignature search is one of the most exciting prospects for Webb. On Earth, oxygen in the atmosphere is produced almost entirely by life through photosynthesis. If we could detect oxygen in another planet's atmosphere, along with other gases like methane that react with oxygen, it would be strong evidence for biological activity. Other potential biosignatures include combinations of gases that don't make sense unless life is present to constantly replenish them. Webb doesn't have the capability to study Earth-sized planets around Sun, like stars, which would be the most promising targets for finding life. But it can study larger planets or planets around smaller, cooler stars where the habitable zone is closer in and planets are easier to observe. The first images from Webb were released during a carefully orchestrated public event. The White House held a preview, and then NASA revealed the full set of images in a televised broadcast. The response was immediate and overwhelming. Social media exploded with reactions. News outlets around the world covered the release, and people everywhere marveled at the beauty and significance of what they were seeing. The images became instant icons, shared millions of times, and viewed by hundreds of millions of people. This public engagement was by design. NASA and its partners understood that Webb represented a major investment of public funds. Communicating the results to taxpayers was essential. But beyond accountability, there was a genuine desire to share the excitement of discovery with everyone. Space science has the power to inspire, to make people think about big questions, and to unite people around common goals. The first images succeeded brilliantly in this regard, capturing public imagination in a way that few scientific events ever do. The educational impact of Webb's first images has been significant. Teachers around the world use the images in classrooms to teach students about space, light, and scientific discovery. The images sparked curiosity in young minds, potentially inspiring the next generation of scientists and engineers. Educational materials were created to help people understand what the images showed and why it mattered. Museums and planetariums featured the images in exhibits and shows. The images became a cultural touchstone, appearing not just in scientific contexts, but in popular media and art. The accessibility of Webb's data is another important aspect of the mission. All of Webb's observations are made publicly available after a brief proprietary period. This means scientists anywhere in the world can access the data and conduct their own analyses. Many discoveries using Webb data come from researchers who weren't part of the original observation teams. This open data policy maximizes the scientific return from the mission and promotes international collaboration. The proprietary period, typically 6 to 12 months, allows the scientists who plan the observations time to analyze their data and publish results before others can access it. This protects the intellectual investment of the teams who designed the observation programs. But after the proprietary period ends, the data becomes available to anyone. This has led to numerous publications from researchers using Webb data for purposes beyond the original intent of the observations. The archival value of Webb's data cannot be overstated. Every observation is preserved and can be analyzed again in the future with new techniques or in combination with new data. Some of the most important discoveries from Hubble came from archival data, sometimes decades after the original observations. As techniques improve and computers become more powerful, old data can be reprocessed to extract information that wasn't accessible when the data was first collected. Webb's data archive will be a resource for astronomers for generations. The computing infrastructure required to handle Webb's data is impressive. The telescope generates enormous amounts of data every day. This data must be transmitted to Earth, processed to remove instrumental effects, calibrated against standard sources, and made available to researchers. The Mikulski Archive for Space Telescopes at the Space Telescope Science Institute handles Webb's data along with data from Hubble and other missions. The archive provides tools for searching, visualizing, and downloading data, making it accessible to researchers worldwide. Data processing for Webb is complex. Raw data from the telescope's detectors must be converted into calibrated images and spectra. This involves correcting for various instrumental effects like detector bias, dark current, flat field response, and cosmic ray hits. The calibration pipeline uses reference files that characterize the telescope's performance. These reference files are regularly updated as the instrument team learns more about how the telescope behaves. The processed data products include calibrated images, extracted spectra, and various quality assessment files that help users understand the data quality. Advanced data analysis often requires going beyond the standard pipeline products. Researchers develop their own software to extract specific information from the data. For example, studying faint galaxies in deep images requires sophisticated techniques to separate galaxies from stars, measure their properties, and estimate their distances. Analyzing exoplanet spectra requires detailed modeling of stellar and planetary properties. The complexity of these analyses is part of what makes Webb science challenging and rewarding. The scientific productivity of Webb has exceeded expectations. In its first year of operations, the telescope conducted hundreds of observation programs covering topics across all of astronomy. These observations led to hundreds of scientific publications. The pace of discovery has been breathtaking, with major results announced regularly, and this productivity shows no signs of slowing. The telescope is healthy and performing excellently, promising many more years of groundbreaking observations. The demand for Webb observing time far exceeds availability. Astronomers propose observation programs through a competitive process. Proposals are reviewed by panels of experts who evaluate the scientific merit, feasibility, and broader impacts. Only about 20% of proposed programs receive time. This high oversubscription rate reflects the unique capabilities of Webb and the enthusiasm of the scientific community. Observers who receive time are under pressure to make the most of it, knowing how competitive the process is. The observation programs conducted with Webb cover an incredible range of topics. Some study the earliest galaxies and the formation of the first stars. Some observe nearby galaxies to understand their structure and evolution. Some focus on star formation and molecular clouds. Some study the death throes of massive stars. Some characterize exoplanet atmospheres. Some observe objects in our own solar system, including planets, moons, asteroids, and comets. The breadth of science enabled by Webb is remarkable, touching every area of astronomy. One of Webb's key science goals is understanding the formation and evolution of galaxies. This requires observations at many distances, looking at galaxies at different stages in their development. By combining observations of nearby galaxies with those of distant galaxies, scientists can piece together the story of how galaxies grow, merge, and change over cosmic time. Webb's infrared sensitivity allows it to study galaxies that are heavily obscured by dust, revealing star formation that would be invisible at optical wavelengths. Another key goal is studying the birth and death of stars. Webb can peer into dense molecular clouds to watch stars forming and observe the remnants of stars that have died. Understanding the full life cycle of stars is crucial for understanding how elements are created and distributed, how planetary systems form, and how galaxies evolve. Webb's observations are filling in gaps in our knowledge and revealing new phenomena that weren't anticipated. Perhaps the most exciting goal is characterizing exoplanets and searching for habitable worlds. Webb is observing dozens of exoplanets, measuring their atmospheric compositions, temperatures, and cloud properties. Each new characterization adds to our understanding of how planets form and what factors determine their properties. The ultimate goal is detecting biosignatures on a rocky planet in the habitable zone of its star. While Webb may not achieve this goal itself, it's paving the way for future missions that will have this capability. Webb's solar system observations are also valuable. The telescope has studied the atmospheres of Mars and the giant planets. It has observed moons, including Saturn's moon Titan and Jupiter's moon Europa. It has characterized asteroids and comets. These observations complement data from planetary spacecraft, providing context and filling in details. For example, Webb's observations of Europa provided information about surface composition that helped interpret data from the Juno spacecraft. The international collaboration aspect of Webb continues through its operational phase. Time on the telescope is allocated to scientists from partner nations based on their contributions to the mission. American astronomers receive time through NASA. European astronomers receive time through the European Space Agency. Canadian astronomers receive time through the Canadian Space Agency. This international partnership ensures that the benefits of the mission are shared broadly and that diverse perspectives contribute to the science. The operational lifetime of Webb depends primarily on its fuel supply. The telescope uses fuel to maintain its orbit at the second Lagrange point and to desaturate reaction wheels that control its pointing. At launch, Webb carried enough fuel for about 10 years of operations, though precise fuel usage is monitored continuously. Based on current projections, the fuel supply should last significantly longer than 10 years, possibly 20 years or more. This extended lifetime would allow for an enormous scientific legacy. Eventually, Webb will run out of fuel and will no longer be able to maintain its orbit or pointing. At that point, the mission will end. The telescope will slowly drift away from the second Lagrange point, becoming just another piece of space debris in solar orbit. There's no plan to retrieve it or decommission it actively. It will simply become a monument to human ingenuity floating in space, having completed its mission of revealing the secrets of the universe. The legacy of Webb extends beyond its specific scientific discoveries. The telescope represents an achievement in engineering, project management, and international cooperation. It demonstrates what's possible when nations work together on ambitious goals. It shows that patient, long-term investment in science and technology pays off. And it inspires people to imagine what else might be possible if we continue pushing the boundaries of what we can achieve. The role of Webb in the broader astronomical community is significant. While Webb is a transformative telescope, it doesn't work in isolation. Its observations are complemented by data from other telescopes across the electromagnetic spectrum. Radio telescopes, optical telescopes, and X-ray telescopes all provide different views of the same objects. By combining data from multiple wavelengths, scientists can build comprehensive pictures of astronomical phenomena. Webb's infrared observations fill a crucial gap in wavelength coverage, revealing details that are invisible at other wavelengths. Ground-based telescopes remain important even in the era of Webb. While space telescopes avoid atmospheric distortions, ground-based telescopes can be much larger and are easier to upgrade and maintain. The largest ground-based telescopes have mirrors 30 meters across, nearly 5 times the diameter of Webb's mirror. These giants can collect enormous amounts of light, enabling studies of very faint objects. Adaptive optics systems can partially compensate for atmospheric distortions, allowing ground-based telescopes to achieve resolution approaching that of space telescopes. The synergy between ground and space-based observations is crucial for advancing astronomy. The extremely large telescope under construction in Chile will have a 39-meter mirror when it becomes operational. This telescope will complement Webb beautifully, providing high-resolution observations at optical and infrared wavelengths. Together, these facilities will enable studies impossible with either alone. For example, Webb might identify an interesting distant galaxy, and the extremely large telescope could follow up with detailed spectroscopy to study its properties in depth. Radio astronomy also plays a crucial complementary role. Radio telescopes can observe cold gas and dust that emit little light at other wavelengths. The Atacama Large Millimeter Array in Chile consists of 66 radio dishes working together to create detailed images at millimeter wavelengths. These observations reveal the raw material from which stars and planets form. By combining ALMA observations with Webb observations, scientists can study both the cold material and the hot, newly formed stars simultaneously. X-ray observatories like the Chandra X-ray Observatory observe the hot universe. X-rays come from extremely energetic phenomena like supernova remnants, hot gas and galaxy clusters, and material falling into black holes. Webb observes some of these same objects in infrared, providing a complementary view. For example, a supernova remnant might emit X-rays from the shockwave, expanding through space, while also emitting infrared from dust, heated by the explosion. Observing both wavelengths gives a complete picture. The multi-wavelength approach to astronomy has become standard practice. Modern astronomical surveys often involve coordinated observations at many wavelengths. Large collaborations bring together experts in different areas to analyze the combined data. This approach maximizes scientific return and leads to insights that wouldn't be possible from any single wavelength. Webb is a crucial part of this multi-wavelength ecosystem, providing capabilities that no other current or planned telescope can match. The future of space astronomy includes several missions that will complement or extend Webb's capabilities. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have a field of view 100 times larger than Webb. While it won't match Webb's sensitivity for the faintest objects, Roman will survey large areas of sky efficiently. This makes it ideal for finding rare objects that Webb can then study in detail. The two telescopes will work together, with Roman as a finder and Webb as a detailed characterizer. Other proposed missions would observe wavelengths that Webb doesn't cover. Far infrared telescopes could study the coldest dust in the universe. Ultraviolet telescopes could observe hot stars and active galaxies. New X-ray observatories could study high-energy phenomena with improved sensitivity and resolution. Each of these missions would address scientific questions that Webb can't answer alone, continuing the tradition of building a comprehensive view of the universe through observations at all wavelengths. The technological development required for future missions builds on lessons learned from Webb. Each new space telescope pushes technology in new directions. Larger mirrors require new fabrication and deployment techniques. More sensitive detectors require advances in materials and cryogenics. Better control systems require more sophisticated software and electronics. The experience gained from developing, launching, and operating Webb will inform the design of future missions, helping them avoid pitfalls and incorporate improvements. Scientists are already thinking about what comes after Webb in terms of infrared space astronomy. Concepts for a Webb successor include ideas for telescopes with even larger mirrors, perhaps 15 or 20 meters across. Such a telescope would require new deployment mechanisms and potentially assembly in space. The scientific capabilities would be extraordinary, allowing studies of Earth-sized planets, around sun-like stars, and direct imaging of the earliest galaxies. But the technical challenges are daunting, and such a mission wouldn't fly for decades. The broader context of Webb includes the role of astronomy in society. Why do we spend billions of dollars looking at distant galaxies and alien planets? The immediate practical benefits may seem limited, but the long-term value is profound. Astronomy advances our fundamental understanding of nature. It inspires people to think about big questions. It drives technological innovation, and it provides perspective on our place in the cosmos. These benefits justify the investment many times over. The economic impact of space astronomy extends beyond the direct employment of scientists and engineers. Companies that supply components for telescopes develop expertise valuable in other markets. The technologies developed for space missions often find applications in medicine, industry, and national security. The inspiration provided by missions like Webb motivates students to pursue careers in STEM fields, building the skilled workforce needed for a technology-driven economy. These indirect benefits add up to significant economic value. The cultural impact of Webb's discoveries is harder to quantify, but no less real. The images from Webb have become part of our collective visual culture, appearing in everything from museum exhibits to music videos. They shape how people think about the universe and humanity's relationship to it. They provide common reference points for conversations about space and science, and they contribute to a sense of shared human achievement, showing what we can accomplish when we work together on ambitious goals. The philosophical implications of Webb's observations are profound. By revealing the early universe and the atmospheres of alien worlds, Webb addresses questions that have occupied philosophers for millennia. How did the universe begin? Are we alone? What is our place in the cosmos? While science cannot answer these questions definitively, it provides increasingly detailed empirical information that constrains possible answers. Webb's observations of ancient galaxies tell us about cosmic origins. Its characterization of exoplanets informs debates about the prevalence of life. Religious and spiritual perspectives on Webb's discoveries vary widely. Some see the images as revealing the handiwork of a creator, marveling at the beauty and complexity of the universe. Others see them as evidence of a purely natural cosmos operating according to physical laws without need for supernatural intervention. Still others find ways to integrate scientific discoveries with religious faith, seeing no fundamental conflict between understanding the physical universe and maintaining spiritual beliefs. Webb's discoveries don't resolve these debates, but they provide new information that people of all perspectives must consider. The future discoveries that Webb will make remain unknown. This is both frustrating and exciting. Scientists have plans for thousands of hours of observations, but the most exciting results are often the surprises. Observations intended to study one thing sometimes reveal something completely unexpected. The history of astronomy is full of serendipitous discoveries where looking for one thing led to finding something else entirely. Webb will undoubtedly produce more surprises as it continues operating. Looking back at the first images years later, their significance is clear. They weren't just a demonstration, they were the beginning of a new era in astronomy. They showed that Webb worked brilliantly and that the universe was ready to reveal its secrets. They inspired scientists to ask bigger questions and design more ambitious observation programs, and they captured the public imagination, reminding people why space exploration matters. The secrets hidden in those first images launched thousands of research projects that continue today. They set the standard for everything that followed, and they ensured that Webb's legacy would extend far beyond its operational lifetime. These images will be studied and admired for generations, standing as monuments to human curiosity and our drive to understand the cosmos. The 5 secrets they revealed were just the beginning. The universe holds countless more secrets, and Webb is revealing them one by one. That's why the first images still matter, and why they will continue to matter for decades to come. The technical specifications of Webb reveal why it was able to uncover these secrets. The telescope's primary mirror has a collecting area of 25 square meters, giving it 6 times more light-gathering power than Hubble. This increased sensitivity allows Webb to detect objects that are significantly fainter. Combined with its infrared capability, this means Webb can see objects that are both distant and heavily obscured by dust. The mirror's gold coating is optimized for infrared wavelengths, reflecting over 98% of the infrared light that hits it. The telescope's 4 scientific instruments each serve specific purposes. The near-infrared camera is Webb's primary imager, taking pictures at wavelengths from 0.6 to 5 microns. This instrument captured most of the iconic first images, including the Deep Field and the Carina Nebula. Its detectors are extremely sensitive, capable of detecting individual photons arriving from distant galaxies. The near-infrared spectrograph splits light into spectra, revealing the chemical composition, temperature, and motion of objects. This instrument was used to study Stephan's quintet and characterize the exoplanet atmosphere. The mid-infrared instrument extends observations to longer wavelengths, from 5 to 28 microns. These longer wavelengths reveal cooler objects and can penetrate even denser dust. This instrument includes both an imager and a spectrograph, providing flexibility in observing strategies. The fine guidance sensor keeps the telescope precisely pointed at its target, compensating for tiny disturbances that would blur the images. This sensor achieves pointing stability better than 1/100th of an arcsecond, which is like being able to aim at a specific human hair from 2 miles away. The cooling system that keeps Webb cold enough to function is an engineering marvel. Passive cooling from the sunshield brings most of the telescope to about -200 degrees Celsius, but the mid-infrared instrument needs to be even colder to function properly. It uses an active cooling system with a cryocooler that circulates helium to remove heat. This cryocooler must operate reliably for the entire mission lifetime with no possibility of repair or maintenance. The fact that it works flawlessly demonstrates the incredible engineering that went into Webb. The communication system that sends data from Webb to Earth is equally impressive. The telescope is too far away for real-time control. Commands sent from Earth take about 5 seconds to reach Webb, and telemetry takes another 5 seconds to return. This means that the telescope must operate autonomously most of the time, following pre-programmed instructions and responding to problems without human intervention. The software that controls Webb is sophisticated, monitoring hundreds of parameters and making adjustments to keep everything operating properly. Data is transmitted to Earth using radio signals at a rate of up to 28 megabits per second when the telescope can communicate with the Deep Space Network antennas. Each day, Webb generates about 57 gigabytes of science data. This data must be stored on board until it can be transmitted, requiring reliable memory systems that can survive radiation and extreme temperatures. Once received on Earth, the data goes through the processing pipeline before being made available to astronomers. The entire chain from photons arriving at the mirror to calibrated data products delivered to scientists involves dozens of complex steps, each of which must work correctly for the mission to succeed. The operational efficiency of Webb is carefully optimized. The telescope's orbit at the second Lagrange point allows continuous observations without Earth or the Moon blocking the view. However, the telescope's orientation is constrained by the need to keep the sun shield between the telescope and the sun. This means that any given target is observable only during certain times of year when it's in the right direction. Observation planning involves complex scheduling to maximize science return while respecting these constraints. The scheduling process balances urgent programs like transient events with long-term surveys and regular calibration observations. Target acquisition is a critical process for Webb. Before observing a faint galaxy or exoplanet, the telescope must point precisely at the target. This involves first finding bright guide stars that the fine guidance sensor can track. The telescope slews to point the guide stars into the fine guidance sensor's field of view, then uses them to maintain precise pointing. For the faintest targets, the guide stars themselves might be at the limit of detection, requiring careful planning to ensure successful observations. Each observation begins with this acquisition phase before the science instruments start collecting data. Calibration is an ongoing process throughout Webb's mission. The telescope's performance changes slowly over time as materials outgas and temperatures fluctuate. Regular calibration observations monitor these changes and update the calibration files used to process science data. Standard stars and other well-characterized objects are observed regularly to track instrument performance. This calibration data is crucial for ensuring that scientific measurements are accurate and that results from different observation times can be compared reliably. The observing efficiency of Webb is high. The telescope spends about 80% of its time collecting science data, with the remaining time used for slewing between targets, acquiring new targets, calibrating instruments, and maintaining the spacecraft. This high efficiency reflects careful planning and optimization of operations. Every hour of Webb's time is precious, so minimizing overheads is important for maximizing scientific productivity. The safety systems built into Webb protect the telescope from potential hazards. Micrometeorite strikes are a concern for any space telescope. While the odds of a catastrophic impact are low, smaller impacts are inevitable over the mission lifetime. Webb's mirrors are designed to tolerate small impacts without significant degradation. The mirrors have redundancy, with 18 segments that can be individually adjusted. If one segment is damaged, the others can partially compensate. Software monitors the telescope's health continuously, watching for anomalies that might indicate problems. If a serious problem is detected, the telescope can autonomously enter a safe mode where it stops science observations and orients itself to protect critical systems. The Mission Operations Center at the Space Telescope Science Institute monitors Webb continuously. Teams of engineers and scientists work around the clock to keep the telescope operating. They plan observations, send commands, monitor telemetry, and respond to any issues that arise. The operations team includes specialists in various areas from attitude control to data systems. When something unexpected happens, these experts diagnose the problem and develop solutions. The smooth operation of Webb reflects the skill and dedication of this team. The scientific community's engagement with Webb extends beyond just using the telescope. Many astronomers serve on panels that review observing proposals, allocate time, and provide advice on mission priorities. Others work on instrument teams, developing and maintaining the software that controls the instruments and processes their data. Still others contribute to outreach and education, helping the public understand Webb's discoveries. This broad engagement ensures that the mission serves the needs of the astronomical community and maintains strong support. The impact of Webb on specific subfields of astronomy has been transformative. In the study of high redshift galaxies, Webb has opened up a new frontier. The most distant galaxies detected by Hubble were at redshifts around 10, corresponding to when the universe was about 500 million years old. Webb routinely observes galaxies at redshifts of 10 to 15 and has detected candidates at even higher redshifts. These observations probe the epoch when the first galaxies formed, providing crucial information about this poorly understood era of cosmic history. In stellar astrophysics, Webb's ability to observe through dust has revealed previously hidden populations of stars. Massive young stars are often deeply embedded in their natal molecular clouds, making them invisible at optical wavelengths. Webb can detect these stars and study their properties, improving our understanding of how massive stars form and evolve. The telescope has also studied evolved stars in their final stages, observing mass loss processes and the creation of dust in circumstellar shells. These observations inform models of stellar evolution and the chemical enrichment of galaxies. In planetary science, Webb has studied solar system objects with unprecedented detail. Observations of Mars revealed details about atmospheric circulation and seasonal changes. Studies of the giant planets showed structure in their atmospheres and measured the abundances of various molecules. Observations of icy moons probed their surface compositions, searching for organic molecules that might indicate subsurface oceans. Asteroids and comets were studied to understand their formation and evolution. These solar system observations complement data from planetary spacecraft and provide context for understanding planets around other stars. In the field of exoplanets, Webb has characterized atmospheres across a wide range of planet types. Hot Jupiters like WSP-96b were early targets because their large atmospheres make them relatively easy to study. But Webb has also observed smaller planets, including super-Earths and mini-Neptunes. Each new characterization refines our understanding of how planet atmospheres form and evolve. The detection of water vapor, methane, carbon dioxide, and other molecules reveals the chemical inventory of these worlds. The presence or absence of certain molecules constrains models of planet formation and atmospheric chemistry. The study of transiting exoplanets has advanced rapidly with Webb. The telescope can observe multiple transits of the same planet to search for variations that might indicate weather patterns, moons, or rings. It can measure the precise shapes of spectral features to determine temperatures and pressures at different atmospheric levels. And it can look for signatures of photochemistry, chemical reactions driven by ultraviolet light from the host star. All of this information builds toward the ultimate goal of characterizing potentially habitable planets and searching for signs of life. The direct imaging of exoplanets is another capability Webb is developing. For planets that orbit far enough from their stars, it's possible to detect their light directly rather than just observing transits. This is challenging because planets are much fainter than their stars. Webb uses coronagraphs that block the star's light, allowing the planet's light to be detected. So far, most directly imaged exoplanets are young, massive, and orbiting far from their stars. But the technique is improving, and future observations may image smaller, older planets closer to their stars. The study of protoplanetary disks has also benefited from Webb. These disks of gas and dust around young stars are where planets form. Webb can observe the structure of these disks in unprecedented detail, revealing gaps and rings that indicate where planets are forming. The telescope can measure the composition of the disk material, showing what ingredients are available for planet formation. And it can detect molecules like water and organic compounds that will eventually be incorporated into planets. Understanding protoplanetary disks is key to understanding planet formation, including how our own solar system came to be. The cosmology results from Webb have implications beyond just understanding galaxy formation. The distances to the most remote galaxies constrain the universe's expansion history. The The properties of early galaxies inform models of structure formation and the nature of dark matter. The abundances of elements in distant galaxies reveal the history of chemical enrichment, and the large-scale distribution of galaxies maps the underlying distribution of dark matter. All of these observations contribute to our understanding of the universe as a whole. The study of gravitational lensing has advanced with Webb. Strong lensing by massive galaxy clusters creates magnified images of distant galaxies, but it also distorts their shapes. By carefully modeling the lensing effect, astronomers can reconstruct the true properties of the background galaxies and measure the distribution of mass in the lensing cluster. Webb's sharp images allow detailed lensing studies that weren't possible before. These studies probe both the distant galaxies being lensed and the dark matter in the lensing clusters. The search for the first stars, known as population 3 stars, is a major goal for Webb. These stars form from primordial gas containing only hydrogen and helium with no heavier elements. Theory predicts they were very massive and short-lived, ending in spectacular explosions that enriched their surroundings with the first heavy elements. No population 3 stars have been definitively identified yet, but Webb is searching. Finding even one would be a major discovery, providing a direct look at the earliest era of star formation. The study of galaxy clusters extends beyond using them as gravitational lenses. Clusters are the largest gravitationally bound structures in the universe, containing thousands of galaxies and vast amounts of hot gas. Webb observes cluster galaxies to understand how environment affects galaxy evolution. Galaxies in dense clusters experience interactions and mergers more frequently than isolated galaxies. They also move through the hot intracluster gas, which can strip away their cold gas and shut down star formation. By comparing cluster galaxies to field galaxies, astronomers learn how environment shapes galaxy properties. The quasar observations with Webb reveal details about supermassive black holes in the early universe. Quasars are among the most luminous objects in the cosmos, powered by black holes accreting material at enormous rates. Webb can study the host galaxies of distant quasars, measuring their masses and star formation rates. This reveals the connection between black hole growth and galaxy growth. Webb can also study the structure of gas around quasars, including outflows driven by the black hole's energy output. These outflows can affect the entire galaxy, regulating both star formation and black hole growth. The study of supernova remnants benefits from Webb's infrared capabilities. When massive stars explode, they leave behind expanding shells of gas enriched with heavy elements created during the star's life, and in the explosion itself, these remnants glow in infrared as dust forms in the cooling gas. Webb can detect this emission and map the distribution of different elements. This reveals how thoroughly the explosion mixed the stellar interior and how efficiently dust forms in the harsh environment of the remnant. The observations of active galactic nuclei with Webb probe the environments around feeding supermassive black holes. These regions are often obscured by thick dust that blocks optical light. Webb's infrared vision penetrates the dust, revealing the structure of the accretion disk and surrounding material. The telescope can measure the black hole's mass, accretion rate, and the properties of outflows and jets. Understanding active galactic nuclei is important because they represent a major phase in galaxy evolution when black holes and their host galaxies grow together. The cosmic web is the large-scale structure of the universe, with galaxies arranged along filaments surrounding vast voids. Webb contributes to mapping the structure by measuring distances to thousands of galaxies. The three-dimensional distribution reveals how structure has evolved over cosmic time. Early in the universe, the cosmic web was just beginning to form. Today, it's fully developed with clearly defined filaments and voids. Observing how the structure changed helps test models of structure formation and constrain cosmological parameters. The dark matter problem is one of the biggest mysteries in physics. We know dark matter exists because of its gravitational effects, but we don't know what it's made of. Webb doesn't detect dark matter directly, but its observations constrain dark matter properties. The formation history of galaxies depends on how dark matter clumps. The distribution of dark matter in galaxy clusters affects gravitational lensing. By measuring these observable effects, Webb helps narrow down the possibilities for what dark matter might be. The dark energy problem is equally mysterious. Dark energy is causing the universe's expansion to accelerate, but we don't know what it is. Webb contributes to dark energy studies by measuring distances to supernovae and galaxies. These measurements constrain the expansion history of the universe, which depends on the properties of dark energy. While Webb alone cannot solve the dark energy puzzle, it contributes important data that complement other dark energy experiments. The connection between Webb's science and fundamental physics is profound. The observations test our understanding of gravity, thermodynamics, nuclear physics, and quantum mechanics. They probe conditions of extreme temperature, density, and gravity that cannot be reproduced in laboratories. They reveal phenomena that push the boundaries of known physics. In this sense, astronomy serves as an experimental laboratory for physics, testing theories in regimes where terrestrial experiments cannot reach. The human side of Webb's mission deserves recognition. Thousands of people worked on the project over more than 2 decades. Engineers designed and built the hardware. Scientists planned the instruments and observation programs. Technicians assembled and tested components. Project managers coordinated the work. All of these individuals contributed their expertise and dedication to making Webb succeed. The telescope represents not just technological achievement, but human achievement, showing what we can accomplish through collaboration and perseverance. The diversity of the Webb team has been a strength. People from many backgrounds, cultures, and perspectives contributed to the mission. This diversity brings different ways of thinking about problems and increases the range of solutions considered. Efforts to increase diversity in astronomy continue, recognizing that the field benefits from including people with varied experiences and viewpoints. Webb serves as an example of how large, collaborative projects can bring together diverse teams to achieve extraordinary results. The training of the next generation of astronomers is influenced by Webb. Graduate students working with Webb data gain experience with cutting-edge techniques and address exciting scientific questions. This hands-on experience prepares them for careers in astronomy and related fields. Many future leaders in the field are current students and postdocs working with Webb. The mission's impact on education and training extends far beyond the direct scientific results. The technological spin-offs from Webb extend into many areas. The mirror polishing techniques developed for Webb have applications in making optical components for industrial and medical uses. The cryogenic systems have applications in areas ranging from quantum computing to medical imaging. The image processing algorithms have applications in fields like medical diagnosis, where detecting faint features in noisy data is crucial. The project management and systems engineering approaches developed for Webb inform other large, complex projects. These indirect benefits add substantial value beyond the direct scientific returns. The policy implications of Webb's discoveries touch on questions about funding priorities and international cooperation. The mission demonstrates the value of long-term investment in basic research. While the immediate practical applications may be limited, the knowledge gained and technologies developed have broad value. The international partnership shows that cooperation on scientific projects can succeed even when nations have disagreements in other areas. This model of cooperation could inform approaches to other global challenges requiring collective action. The public sense of wonder evoked by Webb's images has value that's hard to quantify but nonetheless real. In a world often focused on immediate concerns and problems, the images remind people of the larger context of existence. They inspire a sense of perspective about humanity's place in space and time. They encourage thinking about big questions that transcend everyday worries. This sense of wonder and perspective is valuable for mental health and for maintaining motivation to address long-term challenges. The accessibility of Webb's images and data is important for maintaining public support. The images are freely available in high resolution for anyone to use. Educational resources help people understand what they're seeing. Scientists engage with the public through social media, talks, and interviews. This transparency builds trust and demonstrates accountability for the public investment in the mission. It also creates opportunities for citizen scientists and amateur astronomers to engage with the data and make their own discoveries. As we think about the future, Webb's discoveries will influence the design of future missions and observatories. The unexpected properties of early galaxies motivate plans for even more sensitive instruments. The complexity of exoplanet atmospheres drives development of more sophisticated spectroscopic capabilities. The value of infrared observations justifies continued investment in this wavelength regime. Each discovery shapes priorities for future research and technology development. The connection between Webb and cultural developments extends into art and popular culture. Artists incorporate Webb's images into their work, finding inspiration in the colors and structures revealed by the telescope. Writers use the discoveries as backdrops for science fiction stories, exploring themes of exploration and the search for life. Musicians compose pieces inspired by the beauty and vastness revealed in the images. This cultural engagement shows how scientific discoveries can enrich human creativity and expression across disciplines. The long-term preservation of Webb's data and images is being carefully planned. The data archive will be maintained indefinitely, ensuring that future generations can access and analyze the observations. The images are being preserved in formats that will remain accessible as technology evolves. Documentation of the telescope's design, construction, and operation is being archived for historical purposes. All of this preservation work ensures that Webb's legacy will endure long after the mission ends. The story of Webb's first images is ultimately a story about human curiosity and our desire to understand the universe. From the earliest humans looking up at the night sky and wondering about the lights they saw, to ancient astronomers tracking planetary motions, to Galileo turning his telescope toward the heavens, to Hubble orbiting Earth, to Webb revealing the infant universe, our journey of discovery continues. Each generation builds on the work of previous generations, asking deeper questions and developing better tools to answer them. Webb represents the latest chapter in this ongoing story, but certainly not the final chapter. As long as humans exist, we will continue looking outward and wondering, driven by curiosity about the cosmos and our place within it. The process of selecting targets for Webb's first images involved extensive discussion and debate within the scientific community. Every astronomer had opinions about what should be observed first. Some argued for focusing entirely on the most scientifically important targets. Others emphasized the need for images that would capture public attention. The final selection balanced these considerations, choosing targets that would both advance science and inspire the public. This balance was crucial for ensuring that the first images achieved their multiple goals of demonstrating capabilities, making discoveries, and engaging the broader world. The timing of the first image release was also carefully considered. The telescope needed several months after launch to complete its deployment, travel to its operating location, cool down, and undergo commissioning tests. During commissioning, engineers and scientists systematically tested each component and instrument to verify performance. This process couldn't be rushed because identifying and fixing any problems early was essential. Only after commissioning confirmed that everything worked properly could science observations begin. The first science observations were scheduled immediately after commissioning ended. These observations had been planned years in advance to ensure everything would be ready. The observation plans included detailed specifications of pointing, exposure times, filters, and other parameters. Backup targets were identified in case any primary targets couldn't be observed due to scheduling constraints or technical issues. The entire process was choreographed to maximize efficiency and ensure success. When the observations were complete and the data was processed, there was a final period of preparation before public release. Scientists needed time to analyze the data and prepare explanatory materials. Press releases had to be written, educational resources had to be created, briefings had to be prepared for decision makers and media. All of this work happened under strict security to maintain the surprise for the public reveal. The efforts paid off with a coordinated global release that reached hundreds of millions of people. The immediate response to the first images exceeded even optimistic expectations. Social media platforms saw massive engagement with Webb content. News outlets around the world covered the release prominently. Scientists were inundated with interview requests. The public's hunger for more information about the images and their significance was palpable. This enthusiastic response validated the years of work and investment that went into the mission. In the days and weeks after the first image release, scientific papers analyzing the data began to appear. Some papers focused on specific objects seen in the images. Others addressed broader questions about galaxy formation or star formation or black holes. The pace of publications accelerated as more data became available and as researchers had time to conduct detailed analyses. The first images sparked research programs that continue years later, with new papers still being published based on these initial observations. The citizen science engagement with Webb's data has been notable. Amateur astronomers and space enthusiasts have created their own versions of Webb's images, experimenting with different color schemes and processing techniques. Some have identified interesting objects in the images that professional astronomers might have missed. Online communities have formed around Webb, where people share their enthusiasm and discoveries. This grassroots engagement amplifies the mission's impact and creates lasting connections between the public and space science. The educational materials created based on Webb's first images are being used in classrooms worldwide. Teachers have lesson plans that use the images to teach concepts ranging from light and spectra to cosmic evolution. Students engage with real data from Webb, learning how scientists analyze observations and draw conclusions. Some schools have even connected directly with Webb scientists through virtual visits, giving students the chance to ask questions and hear firsthand about the discoveries. These educational initiatives ensure that Webb's impact extends to the next generation. The challenges of science communication around Webb's discoveries are worth noting. The science is complex and can be difficult to explain in simple terms. Concepts like redshift, infrared light, and spectroscopy require some background to understand fully. Communicators must balance accuracy with accessibility, explaining things simply enough for general audiences while avoiding oversimplification that would be misleading. The Webb team has worked hard to achieve this balance, developing metaphors and analogies that make the science comprehensible without sacrificing essential details. The role of visualization in communicating Webb's results has been crucial. The raw data from Webb is just numbers. Converting those numbers into images requires many choices about scaling, color mapping, and enhancement. These choices affect how people perceive the images and what features stand out. The visualization teams responsible for creating Webb's public images have expertise in both the science and the art of creating effective and beautiful images. Their work bridges the gap between data and public understanding. The comparison between Webb's images and previous images of the same objects helps people appreciate what the new telescope achieves. When the Carina Nebula image from Webb was released alongside Hubble's image of the same region, the increased detail and new features visible in Webb's version were immediately apparent. These before and after comparisons provide concrete evidence of technological progress and justify the investment in new capabilities. They also honor the legacy of previous missions while celebrating current achievements. The interdisciplinary nature of Webb's science is apparent in how researchers from different fields collaborate on analyses. An observation of a distant galaxy might involve cosmologists studying the universe's history, galaxy evolution experts, analyzing the galaxy's structure, spectroscopists measuring chemical abundances, and theorists comparing observations to models. This collaboration across subfields is essential for extracting maximum scientific value from Webb's observations. It also enriches the research by bringing diverse perspectives and expertise to bear on complex questions. The unexpected results from Webb have prompted revisions to theoretical models across multiple areas of astrophysics. When observations don't match predictions, theorists must reconsider their assumptions and explore alternative scenarios. This process of model refinement driven by new observations is how science progresses. Webb is forcing many such revisions, challenging existing theories and pushing theorists to develop better explanations. This theoretical work will continue for years as researchers work to understand all the implications of Webb's discoveries. The technological reliability of Webb has been excellent. The telescope has operated with minimal problems, exceeding performance specifications in many areas. This reliability is the result of thorough testing and conservative design choices during development. The engineering teams anticipated potential failure modes and designed redundancy and workarounds. This careful engineering has paid off with a highly productive mission that has encountered few significant technical problems. The fuel management strategy for Webb aims to maximize mission lifetime. Engineers monitor fuel consumption carefully and plan maneuvers to minimize waste. The precise insertion into the operating orbit and efficient station keeping have conserved fuel beyond initial projections. Current estimates suggest the fuel will last well beyond the original 10-year mission design. possibly enabling 20 years or more of operations. This extended lifetime would multiply the scientific return and make the mission even more cost-effective. The maintenance of Webb's mirror alignment is an ongoing process. The 18 mirror segments must work together as a single optical surface with precision measured in nanometers. Temperature changes and other factors can cause slight misalignments. Engineers regularly use wavefront sensing to measure the alignment and adjust the actuators that control each segment. This process keeps the mirror properly aligned and maintains optimal image quality. The ability to adjust the mirror alignment in orbit is a key feature that enables Webb's performance. The evolution of observation strategies as the team gains experience with Webb has improved efficiency and scientific return. Early observations were cautiously planned with conservative assumptions about performance. As experience accumulated, observers became more ambitious, designing more complex observation programs and pushing the telescope's capabilities. This learning process continues, with each new observation revealing possibilities for future improvements. The community shares knowledge about best practices through workshops and publications, benefiting everyone using the telescope. The serendipitous discoveries in Webb's images highlight the value of deep, high-quality observations. When you observe a patch of sky with unprecedented sensitivity, you often find unexpected things. A search for distant galaxies might reveal an unusual foreground star. An observation of a nebula might capture a background galaxy cluster. These serendipitous finds sometimes lead to the most interesting science, taking research in directions that weren't planned. Webb's exceptional image quality makes it particularly productive for serendipitous discoveries. The role of machine learning and artificial intelligence in analyzing Webb's data is growing. With thousands of galaxies visible in a single deep field image, automated tools are essential for identifying and cataloging objects. Machine learning algorithms can be trained to recognize galaxies, stars, and other objects, classify their types, and measure their properties. These tools enable analyses that would be impossible manually. As the techniques improve, they will allow even more sophisticated scientific use of Webb's data. The comparison of Webb's capabilities to future planned missions helps contextualize what Webb can and cannot do. While Webb is extraordinary, it has limitations. Its field of view is relatively small, making large area surveys time-consuming. Its spectroscopic resolution is good but not the highest possible. Future missions will complement Webb by providing capabilities it lacks. The Roman Space Telescope will survey large areas efficiently. The extremely large telescope will provide higher spectroscopic resolution. Webb is part of an ecosystem of observatories, each with unique strengths. The scientific return from Webb has already far exceeded the investment. The discoveries from just the first few years of operations have advanced our understanding across many areas of astronomy. The images have inspired millions of people and contributed to education worldwide. The technologies developed for Webb have found applications beyond astronomy. By any reasonable measure, the mission has been a tremendous success. And with many years of operations still ahead, the best may yet be to come. The legacy projects using Webb time are designed to create large datasets that benefit the entire astronomical community. These projects observe many objects systematically, creating catalogs and archives that others can use. For example, a project might observe hundreds of galaxies at different distances to study how galaxy properties evolve over cosmic time. The resulting dataset would be valuable not just for the original science goals, but for many other studies that weren't part of the original plan. Legacy programs maximize the long-term value of Webb's observations. The role of Webb in confirming or refuting theoretical predictions is a key part of its scientific value. Time or Knauschleiers. Before Webb, many theories made predictions about what should be observed in the early universe or in exoplanet atmospheres, or in other regimes. Webb's observations test these predictions. When observations match predictions, theories are validated. When observations contradict predictions, theories must be revised. This interplay between theory and observation drives progress in understanding nature. Webb is providing crucial observational tests of many theories. The process of writing observation proposals for Webb is competitive and demanding. Proposers must articulate clear scientific goals, justify why Webb is the right tool, explain their observation strategy, and demonstrate that they can successfully analyze the data. Proposals are reviewed by experts who evaluate their scientific merit and technical feasibility. Only the highest-ranked proposals receive time. This competitive process ensures that Webb's limited observing time is used for the most valuable science. The diversity of science cases for Webb spans an enormous range of cosmic scales. The telescope observes objects in our own solar system just light minutes away. It studies stars and nebulae in our galaxy thousands of light years away. It observes nearby galaxies millions of light years away. And it detects the most distant galaxies billions of light years away, seeing them as they were when the universe was young. This ability to observe across such a vast range of distances and times makes Webb uniquely versatile. The importance of Webb's infrared sensitivity cannot be overstated. Infrared light reveals things invisible at other wavelengths. Cool objects that barely shine in visible light glow brightly in infrared. Dust that blocks visible light is transparent to infrared, and light from the most distant objects stretched by cosmic expansion arrives at Earth in infrared wavelengths. These properties make infrared observations essential for many areas of astronomy. Webb's combination of large mirror and sensitive infrared detectors makes it the premier infrared observatory ever built. The story of Webb's first images is a testament to human ingenuity, curiosity, and determination. Building a telescope of this complexity and launching it successfully required overcoming countless technical challenges. Operating it requires continuous effort from dedicated teams. Analyzing the data requires sophisticated techniques and careful interpretation. And communicating the results requires effective science communication and public engagement. All of these aspects have worked together to make Webb a transformative mission. As we reflect on the secrets revealed in Webb's first images, we're reminded that the universe is full of wonders waiting to be discovered. Each answer leads to new questions. Each solved mystery points to deeper mysteries. The 5 secrets hidden in those first images were just the beginning. The universe has countless more secrets, and Webb is revealing them one by one. That's why the first images still matter, and why they will continue to matter for years to come. They mark the beginning of a new chapter in humanity's quest to understand the cosmos, a chapter that is still being written with each new discovery. The connection between Webb's observations and our understanding of cosmic time is profound. When we look at distant objects with Webb, we're literally looking back in time. Light travels at a finite speed, so the light from a galaxy 13 billion light-years away has been traveling for 13 billion years. We're seeing that galaxy as it was 13 billion years ago, when the universe was less than a billion years old. This time machine aspect of astronomy allows us to observe the history of the universe directly rather than just inferring it from theory. The concept of look-back time helps us understand cosmic history. The universe is currently about 13.8 billion years old. When we observe a galaxy with a look-back time of 13 billion years, we're seeing it when the universe was only 800 million years old. The galaxy's light left when the universe was in its infancy. By observing galaxies at different look-back times, we can trace cosmic evolution. We see how galaxies looked at different ages, how their properties changed, and how they assembled over time. The relationship between distance, redshift, and look-back time is determined by the expansion history of the universe. In an expanding universe, light gets stretched as it travels. This stretching shifts the light to longer, redder wavelengths. The amount of stretching depends on how much the universe expanded during the light's journey. By measuring redshift, we can calculate how much the universe expanded, which tells us the look-back time. Webb's ability to measure redshifts for faint, distant galaxies is enabling detailed studies of cosmic history. The cosmic timeline revealed by Webb spans from the Dark Ages after the Big Bang to the present day. The very earliest epoch, the first few hundred million years, is just beginning to be explored. This is when the first stars formed, ending the Dark Ages and beginning the process of reionization. Webb's detection of galaxies from this era is opening a new window on cosmic dawn. Understanding this epoch is crucial for understanding how the universe transitioned from the smooth, uniform state after the Big Bang to the structured, galaxy-filled universe we see today. The ionization epoch represents a major phase transition in cosmic history. Initially, the universe was ionized because it was too hot for atoms to exist. After recombination, about 380,000 years after the Big Bang, the universe became neutral as atoms formed. This neutral era lasted until the first stars formed. The ultraviolet light from these first stars began ionizing hydrogen again, creating bubbles of ionized gas that expanded and merged. Eventually, the entire universe became reionized. Webb is helping map this reionization process by detecting galaxies at different stages. The chemical evolution of the universe is another key story that Webb is helping tell. The Big Bang created only hydrogen, helium, and tiny amounts of lithium. All heavier elements were created in stars through nuclear fusion and distributed through space by stellar winds and supernova explosions. Over billions of years, the universe has been progressively enriched with heavy elements. By measuring element abundances in galaxies at different ages, Webb traces this chemical enrichment process. The measurements constrain models of how efficiently stars create heavy elements and how efficiently those elements are distributed. The star formation history of the universe shows how the rate of star formation has changed over cosmic time. In the early universe, star formation ramped up as gas collected in galaxies. The star formation rate peaked around 10 billion years ago, when the universe was about 4 billion years old. Since then, star formation has been declining. Most stars in the universe today formed during that peak era. Webb's observations of galaxies at different epochs reveal details of this star formation history, showing when and where stars formed most actively. The mass assembly history of galaxies traces how galaxies grew over time. Small galaxies formed first, then merged to create larger galaxies. The most massive galaxies assembled relatively late, growing through mergers over billions of years. But Webb's observations suggest that at least some galaxies became massive earlier than expected. This finding challenges models of hierarchical galaxy formation and has sparked intense theoretical work to understand how rapid mass assembly could occur. The resolution of this puzzle will improve our understanding of galaxy formation physics. The environmental effects on galaxy evolution are revealed through Webb's observations of galaxies in different locations. Galaxies in dense clusters evolve differently than isolated field galaxies. Cluster galaxies experience more frequent interactions and mergers. They move through hot intercluster gas that can strip away their cold gas. By comparing cluster and field galaxies, astronomers quantify these environmental effects. The feedback processes that regulate galaxy growth are being studied with Webb. Star formation and black hole accretion inject energy into galaxies, heating gas and driving winds. Without feedback, galaxies would convert all gas into stars very quickly. Webb's observations reveal how feedback operates at different epochs. The variability of cosmic objects on different timescales is revealed through repeated observations. Some objects vary over days or weeks, others change over years. By observing the same objects multiple times, Webb reveals what variability tells us about physical processes. The inspiration Webb provides to young people considering careers in science is important. When students see the images and learn about discoveries, some pursue astronomy or related fields. These students become the next generation who will design future missions. The global nature of astronomy demonstrates international cooperation. Scientists from many nations work together, sharing data and insights. This cooperation shows that nations can collaborate effectively on shared scientific goals. The perspective Webb provides on humanity's place in the universe is both humbling and inspiring. We live on one small planet orbiting an ordinary star in a galaxy containing hundreds of billions of stars. We are tiny compared to cosmic scales, yet we can understand this vast universe through science and reason. The questions that remain unanswered drive continued exploration. We don't fully understand how the first galaxies formed. We don't know how common life is. We don't know what dark matter and dark energy are. Each discovery answers some questions but raises new ones. The technological achievements represented by Webb inspire confidence in humanity's ability to accomplish ambitious goals. The telescope required pushing the boundaries of engineering across multiple disciplines. The fact that it worked on the first try demonstrates careful planning, thorough testing, and skilled execution. These same qualities can be applied to other challenges humanity faces. The educational value of Webb extends beyond formal schooling. Adults learning about the discoveries find themselves thinking about fundamental questions. What is our place in the cosmos? Are we alone? How did everything begin? These questions have philosophical and spiritual dimensions that resonate beyond purely scientific interest. Webb's discoveries inform these timeless inquiries even if they don't fully answer them. The impact on future missions is already apparent. Scientists designing next-generation telescopes are incorporating lessons learned from Webb. They're planning instruments that build on Webb's capabilities while addressing its limitations. The technological innovations pioneered for Webb are being adapted and extended for new applications. The mission's success has energized the astronomical community and provided momentum for ambitious future projects. The remarkable legacy of Webb's remarkable first images will endure for many future generations. They represent a historic moment when humanity gained new capabilities to explore the universe. They captured public imagination and advanced scientific knowledge. They set the stage for all the discoveries that followed. Years from now, Webb's first images will stand out as a defining moment, a time when we saw farther and discovered that the universe was even more amazing than we imagined.